everyone, my name is Pranay and I'm from CambiHub. Welcome back to another video, and in today's video we're going to do IGCSE 0478 Computer Science, chapter number 1, data representation. And also we're going to cover the chapter first and practice a lot of worksheets. We're going to finish the whole IGCSE syllabus and practice a lot of past papers to make you ready to appear your IGCSEs. So starting with the topics, this is the printable document that you can get from our forum link, which we'll share in the description. You will be understanding number systems, binary addition, 2's complement, logical shifts, text, sound, images, and file compressions. In today's video, we are going to do all the number conversions. So the first question comes in this chapter is that why do these computers use binary? So these computers have a circuit system. As you all know, this image shows of a circuit system. If it's not clear, the computer contains a motherboard, a circuit, and on that circuit we have these components known as logic gates. We call them logic gates. So what are these logic gates? These are components which allow the computer system to work, and these logic gates only have two states, that is on or off. These logic gates can either be on or these logic gates can either be off. So for on we represent 1 and 0 we use for off. So this is the binary language, and due to these logic gates only we use binary language in computer systems. This is the major reason why we use binary language in computer systems. So if they ask that why is binary used, they contain logic gates, they only have two states, on and off, and that's why we use binary. Moving on to the next topic. The next topic today we have is the number systems. So we have, like in mathematics, we have a number system called denary and decimal number system. The normal numbers we use in our daily life, 1, 2, 3, 4, 5, 6, 7, 8. This is also a number system. In computers also we have three number systems: binary, hexadecimal, and denary. So these all number systems have their own base. As you can see, binary is base 2, hexadecimal is base 16, and denary is base 10. Now what is this base? Let's talk about binary first. So we know binary has two numbers, we have 0 and 1. So since there are two numbers only, we say that binary has a base system of 2, right? Second is denary. So we all know denary. Okay, if you don't know, denary starts from 0 to 9. So there are 10 digits including 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 digits actually. So this is denary. And since there are 10 digits, we call it a base 10 number system. Lastly, we have hexadecimal. Now hexadecimal is a special number system because hexadecimal has all of these digits. It has 0 to 9. But after 9, it has 10 to 15. And all of this, in 10 to 15, we have letters A to F. So essentially, hexadecimal number system looks like this. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So A is 10, B is 11, C is 12, and likewise you'll go ahead. So that's why we call that binary is a base 2 number system, hexadecimal is a base 16, and denary is a base 10. There is one mistake which I would like to point out here. This row has to go here and this has to go here. So please do not get confused by looking at that. Moving on to the next topic for today we have is number conversions. So we all know that in our syllabus we have converting numbers, right? We have converting numbers, and that's what we're going to study right now. So we have binary to denary, denary to binary, binary to hexadecimal, hexadecimal to binary, and then lastly we have hexadecimal to denary and denary to hexadecimal. Right. So these are our number systems. Let's see how do we convert in each of the number systems. Okay, starting off with the questions. If the questions are not clear towards the board, I'm going to write it towards the side so that you can also see. So our first conversion is binary to denary. How do we convert binary to denary? Right, so to convert binary to denary, let's see one example. Our first example is 11000011. 11000011. Remember, each of them is known as a bit, and always in a register we have 8 bits. So always in questions you'll see 8 bits. Let's suppose if it is given to be 11000011. So we have 7 bits here. So we need to put a 0 from here, because whenever we put a 0 from the left side, it does not make a difference. That's why this is called, that's why we say that we need to have 8 bits. Let's see how to convert binary to denary now. Now to convert to binary to denary, what we essentially do is we use a number system known as 1, 2, 4, 8, 16, 24, right? So these are iPhone storage variants. If you are an Apple fan, you must be knowing them. If not, I am going to write them right now. You need to learn them. If you cannot learn them, I am going to tell a trick also. So these are the number system you should know: 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. Till here you should know. This is essentially the number getting doubled, right? So we are multiplying 2. So 2 2s are 4, 4 2s are 8, 8 2s are 16, 32, 64. 64 into 2 is 128, 120 into 2 is 256. So this is a table you need to learn. If you cannot learn, then you can learn it in this way. This is 2 raised to the power 0, this is 2 raised to the power 1, this is 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, 2 raised to the power 5. But since we don't have calculators in computer science, paper 1 is a non-calculator paper, so you need it's recommended that you just simply learn this table. It's going to make your life easier. Okay, let's see how we need to convert this now. What we are going to do is we are going to put a heading value. What is the heading value? So I'm going to start from here and I'm going to start putting 1, 2, 4, 8, 16, 32, 64, 128. Right? Now wherever I have 1, I have 1 here, 1 here, 1 here, 1 here. So wherever I have 1, I'm going to write the denary number which we have just plotted above. So 128 plus 64, and then I have 1 here plus 2 plus 1. Your answer should be 195, right? This is the denary number of this binary number. That is how we convert binary to denary. Let's see another example. So in another example, our number is, okay, let me just guess a side to see the number. Yeah, so our number is 10101011. 10101011, right? We are going to put the heading values once again: 1, 2, 4, 8, 16, 32, 64. Now I can see a 1 here, so I'll write 64. I can see a 1 here, so I'll write 32. It's heading value. I can see 1 here, so I'll write 8. I can see 1 here, so I will write 2 plus 1. Now when you add this, your answer should be around 171. This is the denary number of the binary thingy. Now we have 3 questions in the worksheet. 2 I have given you as an example. The third one you're going to solve and answer in the comment section. If it is not clear, your number is 0001 0001. This is the number, okay, 0001, right? This is the number you need to convert to denary. This is a binary number you need to convert to denary, and share the answer in the chat box, comment box you may say. Okay, the next question is denary to binary. How do we convert denary numbers to binary numbers? We just, whatever we did right now, we need to do the opposite of it, but the process is different. So let us see how do we do 10. So 10 is a denary number. I need to convert denary to binary. How am I going to do that? I am going to do a prime factorization table. So I'll put 10 here. I'll divide it by 2. See, binary is a base 2 number system. That's why we are dividing by 2. So divide by 2, 2 5s are 10. Now I need to write the remainders in order here. So 2 5s are 10. What will be the remainder? Remainder will be 0. 2 2s are 4. Right? What will be the remainder? Remainder will be 1. 2 1s are 2. Remainder will be 0. Starting from the end digit, you are going to move into this order and write your number 1010. This is the binary answer of denary 10. That's how we convert denary to binary. Okay, let's see another example, which is 67. C part of your worksheet that we provide in the description. Right? So we have another number called 67. Okay, we have 67. Right? I've already solved it, so I'm going to look at the sheet, but then you can pause the video and try it out if you want to. So dividing it by 2, we'll divide it by 33, remainder is going to be 1. We'll divide it by 16, remainder is again going to be 1. 2 8s are 16, remainder is going to be 0. 2 4s are 8, remainder is again going to be 0. 2 2s are 4, remainder is again going to be 0. 2 1s are 2, and remainder is again going to be 0. Now as you can see, we'll start from the end digit towards the top. We'll get 1 4 0 0 0 0 0 1 1. Right? So we need to check if our answer is of 4 bits or 8 bits or not. So 1 2 3 4 5 6 7. Now I told you our answer always the register stores 8 bits. So our answer needs to be in 8 bits. So if we add a 0 from here, it won't make a difference. Let's say if we are doing normal maths, I have 20 here. If I add a 0 here, it becomes 200. But if I add a 0 from here, there is no difference, right? So similarly, we need to do in binary numbers. We need to always result our answer to be of 8 bits. So that's a pretty important thing you need to keep in mind. Otherwise, your marks might get cut because your answer always, the register always stores 8 bits. Coming on to the next kind of questions we have is binary to hexadecimal. Now your book has a very complicated table. That's all, you need to ignore that. That is not going to help you. So I'm going to tell you a very easy method through which you can convert binary to hexadecimal easily. Okay, so our first example is 11111111. First let's write hexadecimal. Hexadecimal is a base 16 number system. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, where A is 10, B is 11, C is 12, and likewise. Right, this is hexadecimal number system. Now let's solve. So our question is 11111111, right? Now what I'm going to do is I'm going to use a method known as 8421. 8421. 8421. Okay, let's see. 8421. 8421. Wherever I have ones, I need to add. So this is a special case. I have ones everywhere, so I'm going to add. First of all, I need to divide it into 4 bits, right? So I'll have the answer to be 15 here and 15 here. What is 15 in hexadecimal? It is F, right? So we're going to write F. I know the first example was an exception, so I'll give you more examples so that you don't get confused. This requires a little bit of practice. If you have got the answer, if you have understood how you can solve, you can pause the video and try doing it yourself and then see the answer. So our next example we have is 1100 1100 1100 1100. Again, I'm going to divide it into 4 bits, right? Then 8421 8421. Wherever I have ones, I'm going to add 9, 10, 11, 12, 9, 10, 11, 12. So I've just added 8 plus 4, 8 plus 4 here. So what is 12 in hexadecimal number system? 12 in hexadecimal number system is C. So I'm going to get the answer to be CC. Right? Let's do the last example we have in the worksheet. Right? The last example in a worksheet is 10101010. 10101011. Let's change it a bit so that I can give you a variety of examples. 10101010, you can do in comment section. Okay, so always we are going to divide into 4 bits when doing hexadecimal. 8421 8421. Wherever I have ones, I'm going to add them. 9 10 9 10 11. So A B is my answer. A B is my answer. So that is a very easy method of converting binary to hexadecimal. Now our next kind of questions we get is hexadecimal to binary, the opposite of whatever we have done, we are going to do now. So we are going to do hexadecimal to binary. Let's see our first example. First example is FA, right? FA. My first step will be divided into 2 parts. If I had 3 numbers, suppose 3 to A, this is the hexadecimal I have given. So I will divide it into 3 parts, okay? So I have divided the number into 2 parts. This is my first step while doing hexadecimal to binary. Now I'm going to write 8421, 8421, 8421, right? Now I know F is 15 and A is 10. I know that. So I need to make 15 now. So what combination I will make here to get 15? What can I add so that I get 15? So 9, 10, 11, 12. If I add 8 plus 4, 13, 14, 15. Okay, so if I add all of them, I'm going to get 15, right? If I add all of the headings, I'm going to get 15. So I'll write 1, 1, 1, 1 in front of them. Okay. A is 10. What can I add to get 10? So 8 plus 2 is 9, 10, right? 8 plus 2 is 10. So adding 8 and 2 is going to give me 10. So only in front of 8 and 2, I'm going to write 1. This is the binary number of it. Right? This is the binary number of it. Let's see another example, which is 77. Let's do 76 to get a variety of questions. Rest I have A6 and 77, which you can solve and tell me in the comment section. Let's see what 76 will be. Again, 76 I'm going to divide into 2 parts. I'm going to write 8421, 8421. Right? This is what I'm going to write. Now what I'm going to do is I'm going to see what I can add to get 7. So 5, 6, 7. So if I add all of them, I am going to get 7. So 0, 1, 1, 1. Right? What can I add to get 6? 4, 5, 6. If I add both of them, I am going to get 6. So wherever my combination is being successful, in front of those digits, I am going to write 1. That's it. This is hexadecimal to binary. That's it. Nothing else you need to do. Right? Okay. Moving on, we have, okay, there are more conversions. So let's say if I need to convert hexadecimal to denary now. How will I do that? For doing that, there is no direct method for this, and even if you find someone, it will be division of 16, which is pretty horrible. You know, you do not need to waste time in your exam. And also your answer needs to be correct. So what we are essentially going to do is, we are going to convert hexadecimal to binary and then binary to denary. Hexadecimal to binary and then binary to denary. That's what we are going to do, right? That is an easy method. And if we need to convert denary to hexadecimal, we are going to convert denary to binary and binary to hexadecimal. So what you can do is you can just have a look at this. Okay. I hope that you have noted this down, and this is pretty easy, right? We are going to do more questions on this once we are going to solve our past papers, right? Now our next topic for today is use of hexadecimal number system. Why do we need to use hexadecimal number system? What is the reason? Because computers actually use binary. Then what is the need of using hexadecimal number system, right? Okay. So I'm going to give you time to read this out so that you can understand why do we need to use it. Okay. Coming back to the exercise, let us see. Okay. First reason is that hexadecimal is easy to comprehend and debug. Hexadecimal is easy to comprehend and debug. What is comprehend? Another word for comprehend is understand. So and debug is finding errors. Whenever we find error, it is known as debugging in computer science. Right? So it is easier to understand and find errors. Why? Because binary is such a longer number, 10110111. Hexadecimal is like AF 62. You know, this is a shorter representation. So it is easier for human beings to understand and find errors at the same time. Then it consumes less screen space, which is obvious, right? It's a shorter representation, so it will consume less screen space. And then we have consumes less storage. Obviously, because I have less amount of digits, so it will consume less storage. These are the points which we have written from the marking scheme. If you don't know what a marking scheme is, Cambridge papers have a question paper and a marking scheme. Question paper is essentially where you have the questions which you will get in your exam, and marking scheme is the answers to that which teachers use to check your paper. And marking scheme is considered to be sovereign or the god, because marking scheme is the one through which your answers are going to check. So marking scheme is the god. Anything that is written in the marking scheme is considered to be the truth, right? Because using that only your answers is going to be checked. So if you have written something else which is not there in the marking scheme, there can be exceptions, but if you have written something which is not there in the marking scheme, is not marked, right? Coming back, this is why do we use hexadecimal, right? Now the next question is, where do we actually use hexadecimal in computers, right? That is our next question. So we use hexadecimal firstly for error codes. Wherever you will see error codes in your system, right, you will see in hexadecimal. Then we also use MAC address in MAC address. In further chapters, we are going to understand each one of them, so you do not need to worry about what these things are. Just remember the list wherever hexadecimal is used. IPv6 address, which is IP address. And the fourth option is it is used in HTML color codes. A short description on what each of them is. So error codes, I explained any error that comes in your system and there's a code. If you enter that code onto the website of the system manufacturer, you are going to find a full document where the description of the error would be given. So there we use hexadecimal. Then we also use in MAC addresses. So MAC address is the serial number of your system, right? If you have an Android device, an iOS device, a Mac, whatever you have, Linux, right? If you go to the system settings and try to see the manufactured ID, it is called MAC address. That is your MAC address. The serial number which is fixed, it is given by the manufacturer. So if I have a device of Apple, so a special serial number given to my iPhone or my Mac by the Apple is called MAC address. IP address, IPv6 address, we are going to learn into detail when we come to chapter 5 and chapter 6. So chapter 5 essentially, so you don't, and chapter 3 also, you do not need to worry about IP address right now. Just remember that in IPv6 address we use hexadecimal. Then HTML color code. So HTML is a program, is a coding language, right? It is basically used for creating web pages, websites, web pages, right? There we use HTML. And they also have specific color schemes, color codes, right? There we use HTML color codes, there we use hexadecimal. Right. So this is the last topic, third last topic of today's video, which is addition of binary numbers, right? How do we actually add binary numbers? What is the secret behind them? There's no secret as such. It's pretty easy to add binary numbers, right? Let us see. Okay, so I'm going to scroll down. If you are not able to see, okay, few rules that you need to remember while doing binary addition. 1 plus 0 is 1. 0 plus 1 is 1. But 1 plus 1 is 10. In binary, 1 plus 1 is 10. And if we add triple ones, it becomes 11. These are set of rules you need to remember, right? There is no question why is this. You just need to remember it. Trust me, you just need to remember it and save time in exam. Okay, let's pick up the first question from the exercise. 0001 1101. 0001 1101. Let's add that to 011 00110. 011 right? Let's add them. Let's see what the result is. So 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 10, right? So I'm going to put 0 here and 1 I'm going to take into carryover. This is simple maths. In simple maths also we carry over numbers, right? So 1 plus 1 is 10, I'll take 1 carryover. 1 plus 1 is again 10, I'll take 1 as a carryover. 1 plus 1 is again 10, right? This is your answer, right? I always told you that a register can only store 8 bits. So let's see if this is 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. This is 8 bits, so our calculation is correct. Now let's do one more example and see what happens in this example, right? This is a pretty important example and let's see what happens in this example. Okay. So our example is 0111. We add that to 1101 1110. 1101 1110. Let's add them. Let's see what happens. 1 plus 1 is 1. 1 plus 1 is 10. 1. Now we have 3 ones. It is 11. 1, 10, 1, 11, 1, 10, 1, 11, 1, 10. Is there something wrong with the calculation? Let's count the number of bits. 1, 2, 3, 4, 5, 6, 7, 8, 9. But didn't I tell you that a system can only have, or a register can only store 8 bits, right? This is called an overflow bit, right? This bit is overflowing, that's why we call it overflow bit. It's pretty self-explanatory. And this kind of an error we call overflow error, right? So if you need to define how are you going to define it? When a greater number of bits are produced in the output during the calculation than the register can store. When more number of bits are produced than the register can store, it's called an overflow error, and this is the practical example of it, right? That's it. In binary addition we have nothing. Let's move on to our next thing called logical shifts. Next topic for today is called logical shifts, right? So we have two kind of shifts. We have a left shift and we have a right shift. So there are two kind of shifts. We have a left shift and we have a right shift, right? Okay. Let us see an example. 1001 1001. Okay, it says left shift. We would always be given by the number of places also, how many places we have to shift. See, the question has not given how many places we have to shift, which means we have to shift one place towards left. It is understood, right? So we are doing a left shift. So while we do left shift, in your brain, you need to keep in mind that we have to shift this number towards left. This is my whole number, I'm going to shift it towards left. And when I shift it towards left, what is going to happen? One space will be blank here and this one will be cancelled, right? I had this number, right? I shifted my register here. So as you can see, this one bit is lost, right? This one bit is lost and I have one space empty. I'm going to add a 0 here. This is left shift, right? Let's do one more example of a left shift. Suppose we have 1 0 1 1 0 1 1 0, right? We have this number. We are doing a left shift. We had this number, right? We are doing a left shift, right? We did a left shift. So this 0 is lost and we had a 0 from here, right? Suppose I need to do 4 places. 0 1 1 0 1 1 0 1 2 3 4 5 6 7 8. Suppose I have to shift to 4 places. This is my number. First place, second place, third place, fourth place. First, second, third, fourth. Right? So I have shifted to 4th place, which means I'm going to add 4 zeros here and this whole part is going to be removed from here. Right? This is called a left shift. What if you had to do a right shift? Let's see. What's the question given in the worksheet? For right shift, we have 1 1 1 0 1 1 1 0. Let's do a right shift. This is a number. We need to shift it towards right. So we shift it towards right. This 1 is lost and 1 0 we add here. This is the right shift. Right? I hope it's very easy to understand. Right? You can do this mentally also, but I would always recommend just keep checking it once so that it's just not wrong, because these are scoring questions. We do not want you to lose marks. Now sometimes the question can ask you, what result would the number have if I shift it towards the left or right? Right? Always remember whenever we do a left shift, right, we multiply 2 raised to the power n. Whenever we do a right shift, we multiply 2 raised to the power, we divide 2 raised to the power n. What is happening? Let's understand. Let's see if I have a number a. Right? Let's see if I have number 20. 20 is a denary number. Right? So then this number, I did a left shift in binary format. First you will convert it to binary. I did a left shift of 2 places. So this was my number, 2 places I did a left shift. This was my number, 2 places I did a left shift. This is its denary value. What is going to happen is, I did a left shift. So I'll multiply 20, the number's denary value, with 2 raised to the power n. N is the number of shifts I did. So I did 2 places, so n will be 2. What if I did 3 places? If I shifted the number to 3 places towards left, 2 will be 3. So whatever my binary number is, it's denary number. When I convert my binary number to denary number, its denary number is going to have this change. So if I am shifting a binary number, I'll convert it to denary and this will be my result of that shift. So whenever I do a left shift, the denary number, when I convert binary to denary, whatever the number I have, suppose this number I have to do left shift, I'll convert it to denary, and its denary number is going to have a effect of multiplying factor of 2 raised to the power n. N is the number of shifts I did. So let's say if this is number a, this is binary. Let's say I have this number, right? This is binary, right? I convert, this is the number. I did 4 places left shift. I did 4 places left shift of this number, right? What would happen? Okay, what's the denary of this number? This denary of this number is 10, right? So I did a 4 places left shift to this number. What is going to happen to its denary number? 10 into 2 raised to the power 4, right? Easy. Suppose I did a right shift on this. Suppose I did a 4 places of right shift. Now what would happen is, I would divide 2 raised to the power n. So I would just divide 2 raised to the power 4 because I did 4 places towards right. That's the difference. Whenever we do a left shift, we divide 2 raised to the power the number of shifts. Whenever we do a right shift, we divide it by 2 raised to the power number of shifts. Here we multiply, here we divide. So left multiply, right divide. That's it. This is a logical shift, whatever you need to know, right? If you have any doubts, you can place it in the comment box. I would try to answer maximum number of doubts, maximum number I can. Now the last topic for today is called 2's complement. The last topic for today is called 2's complement. What is 2's complement? Right? Let's directly take an example from here. Let's take 39. This is a denary number. I want you to pause the video, convert it to binary, right? Because now I'm not going to do it because I've already told you many a times. So this is going to be 1. When I convert it to binary, it is going to be 0, 0, 1, 0, 0, 1, 1, 1. 0, 0, 1, 0, 0, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. This is going to be the answer, right? You can do it yourself, right? Now what I'm going to do in 2's complement is, first step to do a 2's complement is, I'm going to inverse the number, which is also known as 1's complement. What is inverse of number? Wherever I have a 0, I'll put 1. Wherever I have a 1, I'll put 0. So I've inverted the number. This is my first step, right? Then I just add a 1. That's it. This is known as the 2's complement form of this number. This is how we do a 2's complement, right? So let's write the steps here. First, we convert to binary. If it's already in the binary, then we skip this step. Then we inverse the number, or we do 1's complement. Then at the end, we add a 1. That's it. This is the process known as 2's complement, which will be asked in your paper, right? Let's do another example. Another number I have is called 88. This is a denary number. I convert it to binary. Pause the video, convert it to binary to yourself. I'm not going to show it. So when you convert it to binary, the number is going to be 0, 1, 0, 1, 1, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, right? This is my binary number. First step, convert to binary, done. Second step, inverse, 1's complement. Okay, 1, 0, 1, 0, 0, 1, 1, 1. Right? Third step, add a 1. I add a 1. 1, okay, I always start from here. 1 plus 1, 10. 1, 10, 1, 10, 1, 1, 0, 1, 0, 1. That's it. This is the 2's complement of the number. Now one homework question I'm giving you is the number, okay, you can try doing 27. Right? Try doing 27 and send the answer in comment box with text, sound and images. So this section basically talks about how is text, sound and images stored as binary in a computer system, right? Let's talk about text first. How is text, whatever we type, whatever you see on the computer system, how is that stored, right? So text is basically stored using a character set, right? This is called a character set. This is the definition of a character set. A set of character where each character has a unique binary value, right? So we have a set of characters A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, and each letter A, B and C, each letter has a unique binary value. This is called a character set. And we have 3 types of character set. Majorly we have ASCII and Unicode, but ASCII also has 2 types, which is ASCII and extended ASCII. So this is a character set. This is how we store text in a computer system. Let's understand what is ASCII. So ASCII full form is American Standard Code for Information Interchange. Right, this is the American version, American character set. It was developed in 1963 to use in communication systems. Not necessarily you need to know this, it's extra information, right? The main thing you need to know is that this is a 7-bit character set, 7-bit codes, right? So the binary value is going to be of 7 bits and 0 to 127 in denary. So maximum number of bits, 7-bit, right? So maximum number of 7-bit is going to be, right? This is the maximum 7-bit number, 1, 2, 3, 4, 5, 6, 7. If you convert that to denary, you're going to get 127. So 7-bit, right? It can store 7-bit codes, binary codes, right? Now what you need to remember, in your book, a whole table is given. What is the binary value of A? What is the binary value of B? You do not need to learn that. An easy trick to learn that is, say, A is 97 in denary. So A is 97. This is the, if you convert it to binary, it is the binary value for A in ASCII, right? So obviously B is going to be 98, C is going to be 99, and likewise you're going to go till Z. right? So if they ask you what is the binary value of letter C in ASCII, so if you know that A is 97, you will reach to C 99. When you convert it to binary, that is going to be the binary value of the letter C in ASCII character set, right? Okay. Similarly, capital A starts with 65, so capital B will be 66, and likewise. That's how you're going to do this question, right? Okay. Moving ahead. Now we are going to study. Okay, this is we missed one thing. This is ASCII. We also have another type of ASCII known as extended ASCII, which has a little bit of extra characters, right? We use characters also, right? Semicolon, colon, these extra characters, right? Now it can store 8-bit codes. Normal ASCII can store 7-bit codes. Extended ASCII can store 8-bit codes, which is 0 to 255 in denary. So what is the maximum binary number, 8-bit binary number? 1, 2, 3, 4, 5, 6, 7, 8. This is maximum 8-bit binary number. If you convert it to denary, it will be 255. So it can store 8-bit binary number 0 to 255 in denary, right? This is what you need to know for extended ASCII. That's it. Nothing else you need to know. This is all extra information given in the book, right? You're going to ignore that. Okay. Let's come to Unicode now. What is Unicode? Unicode is another kind of a number system character set. Now you would say we have ASCII, we have extended ASCII. Why would we need Unicode? So guys, you do texting daily, right? WhatsApp, Instagram, Facebook. There are emojis there, right? So these special characters comes in Unicode. That's why Unicode was developed. These are the reasons why Unicode was developed. Firstly, to create a universal standard which covers all languages. See, ASCII was American, so it would only cover English. But then we have more languages in Unicode, right? This is the first reason. Second reason, produce a more efficient coding system. So Unicode is more efficient than ASCII. Adopt a uniform encoding where each character is encoded as a 16 or 32 bit, right? So we know in ASCII, extended ASCII, we just did that it is 7 or 8 bits. This is 16 or 32 bits, right? Create unambiguous encoding, right? Which means, okay, this is something you need to learn. You do not need to, go into depth into that. These are few points why Unicode is used. The last point is pretty important, which is reservation, right? So what user can actually do is in Chinese and Japanese languages, these are exceptional languages where sometimes people require to create their own character. So what if a character is not there in your keyboard, but you want to create your own character? Unicode character set has blank spaces. So in those blank spaces, you can create your own characters, right? So useful for Chinese and Japanese character sets, right? This is why we use Unicode number system. Image credit goes to Harder Education. This is a picture from your book, right? Let's talk about how sound is saved in a computer system. How a sound file is saved in a computer system. Any physics students out there must be knowing how a sound wave works, right? So we have a wave like this. This is how a wave goes, right? Math students, you must have learned the graph of sine, right? In trigonometry. This is my sound wave. What happens is this is known as my amplitude. This is known as my wavelength from this point to this point. And the amount of waves produced, this is a full wave, right? So amount of waves produced in 1 second is called frequency. Amount of oscillations, we call it oscillations, right? So these three things are there. So computer stores these three things of the sound file, and that's how it saves the sound file. So what it basically does is it uses sampling. What is sampling? So this is my sound file. What it is going to do is it is going to create smaller parts of that file. This is known as sound sampling, and each sample will have a unique binary value. That is how sound is stored in computers, right? So we have a sound sampling, a little piece of sound that is recorded at regular intervals. We record sound according to intervals. We divide the sound wave, we record it according to the interval. Each interval has a unique binary value, right? Sample rate is the number of samples we record per unit time or per second, right? The amount of samples I'm taking per second. I've divided the sound wave. This is one sample. So the amount of samples I'm recording in 1 second is called sampling rate. Sampling resolution is number of bits I assign to each sample, right? So I told you, I divide my I divide my sound into samples. Each sample has a unique binary value. The rate at which I divide is called sampling rate, and the amount of bits I assign to each sample is called sampling resolution. It is pretty simple, right? This is what we need to do. Moving ahead, we have, okay, if the question asks you how is a sound file stored, this is what you need to write. The amplitude of the sound wave is first determined at a set time interval, right? So this is the sampling rate. We first divide our sound into samples. Then we give an approximate representation of the sound wave in the computer system. Then each sample of the sound wave is then encoded into binary digits where we assign bits to each sound wave, known as sample resolution. So this is your answer, which has to be, right? The images above, the credit goes to Cambridge University Press, right? This is from your book, these images that I've taken above, right? So this is sound wave, right? How do we represent? Once again, we divide the sound wave into smaller parts, and each part is known as a sample, and each part is assigned a unique binary value, right? This is sound, how sound is represented. Now, suppose I need to increase the quality of my sound file. I'll just move ahead so that you can read it easily. Okay, what if I need to increase the quality of my sound file, right? What I can do is I can increase the sampling resolution, which means I can assign more amount of bits to each sample to get a richer, to get a clear, crisp, a large dynamic range, right? I need to get a perfect sound. So if I increase the sampling resolution, that is going to happen. But please remember, let's say, okay, these are benefits and drawbacks. First benefit will be dynamic range, right? I can record richness into my sound file. If I give more bits to it, very small details to that sound file, right? Each and every background noise, everything would be audible. So more higher quality sound wave I will obtain, a larger dynamic range, right? However, drawback is it will consume a larger storage file because we are assigning more bits, more amount of bits stored in my computer system. The sound file is going to take a larger storage, right? Requires greater processing power. This is another drawback. First of all, another advantage is obviously if I increase my sample resolution, it is going to increase my sound quality, dynamic range. But another drawback is that it will require more processing power to store, right? What if my system is very weak? It cannot give more bits. It cannot store more sound resolution. Then what? Then it will reduce sound distortion. What is sound distortion? Sometimes if you are recording sound in your mobile, you must have seen there might be some drizzling of the sound, or there might be some wiggling, right? That is known as distortion, right? Benefit will be less sound distortion, but again, it will take a longer time to upload and download the file over the internet. If the file size is greater, then wouldn't I take a longer time to upload and download over the internet if I need to share it with my friend? And if I provide a larger sampling resolution, the file size will be bigger. It will be difficult for me to share. My email will also, email app, Gmail, right? If you use Gmail, it will say that you need to upload it to Google Drive first and then you can transfer. So it's going to create more problems, right? Then better production flexibility, right? You can easily edit. If you do video editing, audio editing, right? If I provide a larger sampling resolution, my sound will be more rich. So my flexibility of editing that file will be easy. However, another drawback will be that the file can get corrupt. What is the meaning of corrupt? If I store too many bits, sometimes a computer might not be able to handle it, and it may fail to decode and show the sound file to you. So that is a drawback. Okay. Talking about images. How are images stored in a computer system? Right. Okay, let's say if I have my image here. This is my image. I need to store this image in my computer. What I'm going to do is, I'm going to divide this image into smaller parts. So I made a matrix, I've made a grid, I've divided the image into smaller parts. Each part is called a pixel. Each part is called a pixel. If they ask you to define a pixel, pixel is the smallest component of an image or smallest square shaped part of an image. It can be circular also. These images are known as bitmap images. In our syllabus, we are studying bitmap images, right? So this is a small pixel, right? So I've divided my images into grids. A smaller part I've taken out, and each part is assigned a unique binary value. Okay. Now there are two things. First is I'll assign a binary value to the whole pixel, plus each of the pixel will have a different color, right? Bitmap images are colored images, right? There are only three colors that exist in a computer system, which are known as RGB: red, green, blue. Mixing these colors, right? These are primary colors, you must know if you're an art and design student. If you mix these colors, you can make different kind of colors. You can make black, white and stuff, right? So mixing these colors, you can make a lot of colors. So computers use RGB color scheme, right? Now, first thing I told you that I'm going to give few amount of bits, right? I'm going to store this in binary, so I'm going to give each unique binary value to each pixel. I'm also going to provide bits to its color, right? So the amount of bits I provide to its color is called the color depth, right? Because the more amount of bits I'll provide to the pixel for its color will be more rich. So these are few things you need to remember. Okay, metadata of an image is the image resolution or color depth. So what is resolution? Resolution is the dimensions of an image. We know what is resolution, dimension of an image. If I ask what is the resolution of this whiteboard, right, you might say 10 by 10 inches, whatever, right? The one's normal computer system, your screen in your laptop is 1024 into 1080p, 1080, 1024 into 1080 resolution. We call it 1080p. We have 4K, right? This is resolution of screen size. We also have resolution for an image. So the number of pixels wide by number of pixels high, length into breadth, that is an image resolution. That is the area it will cover, right? Pixel is a very small dot of color that is displayed with many others in an image. We just did that, right? And what is color depth? Color depth is amount of bits I provide to color in a pixel is known as color depth. I hope you have understood how an image is stored in a computer system. Simple. We have an image. We divide the image into smaller parts called pixels. Each pixel has a unique binary value. We provide bits to its color called color depth. And we also calculate its number of pixels wide by number of pixels high, which is its image resolution. That's it. Nothing else. You can note down the points, repeat the video, rewind the video I would say, and note down the points, right? Okay, we have done this. Color depth also we have done. This is extra information. You do not need to know this. If you want to read it, you can pause the video and read it, or you can click on the link in the description to find these notes or worksheet, you may say. Image resolution, file size. Yeah, coming to file size. Like for sound, we studied that higher resolution means higher quality, but then higher storage space. Same with images, right? Higher color depth. If I give more bits to my color will be more rich in an image. It will be more sharp, right? I can present vibrant colors in my image then. But then it will increase its file size. So advantages, image is going to be of rich quality, but then file size is going to increase because I'm providing more bits. I'm storing more binary into each pixel. Then larger file size can impact transfer times, downloading or uploading the file, or it can also affect your internal storage. Your system can run out of storage, right? These are some common problems which you may face. Okay. Okay. What happens when you have a lower resolution image? What if I provide less pixels to an image? Okay. Have you ever seen when you try to zoom in your phone, right? If you have an image, you try to zoom it. When you zoom it too much, it gets blurred. That is called pixelated. So if I provide less pixel to my images, when I'm going to zoom it or I'm going to view it normally, it is going to be more blurred. More amount of pixels means image is more sharp, it is more crisp. Less amount of pixels means it is pixelated, it is blurred, right? That's it. Okay, coming to memory storage. Okay, this is the table you need to remember. There is no shortcut to it. Okay. You have heard, right? MB, KB. You must have heard that my system is of 500 gigabytes. If you buy a laptop, it is of 512 gigabytes HDD SSD. That is the storage capacity. That is what we're going to study right now. Okay. 8 bits. Right? One register, 8 bits. Told you that is equal to 1 byte. Understood? Right? 4 bits, half of a byte, 4 bits It's called a nibble. 1 nibble. Right? You need to remember this. What is this? Why is this? No questions. You need to remember this. Okay. Talking about kilobyte. Kilobyte is 1000 bytes. If I get 1000 bytes, it is 1 kilobyte. 1 megabyte will be, I will add 3 more zeros. 1 gigabyte will be, I will add 3 more zeros. 1 terabyte will be, I will add 3 more zeros. 1 PB byte will be, I will add 3 more zeros. 1 exabyte, I will add exabyte, 3 more zeros, right? If you think that this is still used in computer systems, if you're going to say my SSD or my HDD or my internal storage in my laptop is of 512 gigabytes, that is wrong, my friend. We do not use this system anymore. Kilobyte, megabyte, you must have heard this a lot in junior grades. But trust me, your computer does not store this amount, this kind of a thing. Your storage is not in this. Then what do we use? We use a more efficient and a modern system, right? Which is this. Kilobyte, not kilobyte, kibibyte, not megabyte, mebibyte. Kilobyte, mebibyte, gibibyte, xbibyte, tebibyte, pbbyte. This is the new amount of new number system we stored, right? So 1 kilobyte is 1 kb, 1 kibibyte will be 1 kib. Okay, 1 kib is 2 raised to the power 10 bytes. Okay, 2 raised to the power 10 is 1024, by the way. This is maths, right? Okay, 1024 bytes is 1 kib. Now I'm going to take this kib, put it here. 1024 kib. What is the next one? Gib. 1 gib. I'm going to take this gib towards here. 1024 gib is 1 tib. I'm going to take this tib towards here. 1024. Okay. After this, it won't be asked in the exam, but still you should know, right? So this is 2 raised to the power 20 bytes. This is 2 to the power 30 bytes. However, to make things easier, you can learn it in this way. This table in your book is a bit complicated, so you can learn it this way. 1024 bytes is 1 kib. Whatever the next number is, gib, tib, right? So I am going to make a list. Kib, gib, tib, pi. What do we have next? We have tib. Then we have kib. Okay, I am missing one thing. I am doing one thing wrong, which is MIB. I missed MIB. So let's make a list. Let's do it once again. KIB, MIB, GIB, TIB, and then, okay, till here we need to know. What you're going to do is 1024 bytes is equal to 1 KIB. Cut KIB from the list. What is next? MIB. So I'm going to bring this KIB towards here. So 1024 KIB is 1 MIB. Cut this from the list. Now we have GIB. I'm going to bring this MIB here. 1024 MIB is 1 GIB. Cut it from the list. Next we have is TIB. I'll bring GIB here. 1024 GIB is 1 TIB. My friend, that is how you learn this table. You do not need to learn anything. The only number from which you should have love from is 2 raised to the power 10, which is 1024. Right? 2 raised to the power 10, which is 1024. Moving on, our next topic is how do we calculate a file size? How do we calculate file size? You will have image resolution, you will have color depth, always given in the question, right? Image resolution, for example, if they say I have an image of 1024 into 512, right? and the color depth of the image is given to be 124 bits. This is the color depth. So I have my image resolution and I have my color depth, IRCD, right? If they ask me to find the image resolution in bytes, right? First of all, how would I find the file size? I need to find the file size. I'm given with the image resolution and color depth. So I'm simply going to multiply them, 1024 into 512 into 124. That's it. This is going to give me the file size. But this is going to give me the file size in bits. If they ask me to give the file size in byte, 8 bits is 1 byte, so I'm simply going to divide it by 8. Now you will say, how will I do such a long calculation? Right? We don't have calculators. My friend, you should know that table I told you in part 1. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512 and 1024. This table should be like this in your mind. Like this. Okay? Let's see. I have this 8, right? Okay. What we can essentially do is we can divide by 2. We'll divide 2 here and 2 here. 2 4s are 8. 5 1 2. Fine. Yeah, I'm doing half. I'm doing half of this, half of this. 2 2s are 4. 128. 2 1s are 2. 64. That's it. Now you're going to multiply this. Again, they will not give such a large calculation, so you do not need to worry. But trust me, if you know 1, 2, 4, 8, 16, 32, 64, 128 and you are good in maths, you can divide things by 2, multiply things by 2. It would be much easier for you. Okay. Moving on to the next part, this is how we calculate file size of an image. If we need to calculate file size of a mono sound, we have two types of sound. We have a mono sound and a stereo sound. If the question asks you to calculate the file size of a mono sound, we would be given with the sample rate in hertz, sample resolution in bits and the length of the sample. We are simply going to multiply them. Let's say if the question says calculate the file size of a stereo file. So you're going to multiply a 2 here. That's it. The formula is going to remain the same. So for mono, this is the formula. For stereo, a multiplier 2 here. Right? Hope this formula is clear to you. Coming to the last topic, file compressions. What is file compression? What do you think a file compression actually is? Right? So what happens is, if I want to store a large amount of file in my computer system and I wanted to consume less storage, I reduce its file size. I compress it. Right? So there are two types of compression in our syllabus: lossy compression and lossless compression. Lossy, lossless. Lossy, lossless. Two types. Lossy compression. Okay. First of all, what is the definition? Eliminates unnecessary data from the file. The original file cannot be. Okay, this is lossy. So there are two types: lossy and lossless. Right? So name of this compression type is lossy, which means loss of important data permanent loss, irreversible. Whereas lossless, it says it cannot loss, lossless, it is not lossing. So loss of unnecessary data. Temporary loss, reversible. That's it. That's all you need to learn for lossy and lossless. So what are these points saying? First of all, lossy file compression. If I give an image for lossy file compression, it will randomly remove pixels. It will not see. So important data can be lost. It is permanent and it is irreversible. So once I compress the file, that data will be permanently removed and the file size will be reduced. There is no way to recover it. When I talk about lossless, the name is lossless, which means the data will not get lost. So loss of unnecessary data. So what this did was, lossy just randomly deleted data. This will see unnecessary data. So we all know our human ears can only hear till 20 to 20,000 hertz. So if I provide lossless compression, a sound file, it is going to remove all the frequencies that we humans cannot hear. So that is how it reduces file size. So it will remove unnecessary data, and it is temporary. I can reversible. Lossy is fully reversible of file size. I can fully reverse, get the original file, right? One thing is perceptual, perceptual sound shaping. The example that I just gave you, that the humans can only hear till 20 to 20,000 hertz. The rest other frequencies is removed. This kind of a process is called perceptual sound shaping. See, this is something you need to learn. I cannot explain it further. This is what you should know. You need to learn this. Okay. Coming on to the last topic for today. You know, there are some extra information. You can read it once I provide this in the description, right? There is some extra information you do not need to know. You simply need to know, okay, you just need to know, we have dealt with MP3, MP4 files we use in our computer system. So MP3 file is basically, okay, this is your homework. Go to Google, find is MP3 lossless or lossy file compression. Is MP4 lossless or lossy file compression? Is JPEG? I'm giving you the homework. MP3, MP4, JPEG and PNG and JPG. These are the file systems we use in our file types we use in our system. Google which one is lossless and which one is lossy and type in the comment section. I will check it, right? This is your homework. Moving on, our last topic for today is RLE. RLE is a lossless file compression. RLE is a lossless file compression. Lossless compression, it is a type of lossless compression. What does RLE does is, it can only work when I have large amount of repeated data. So let's look at one example. Right? Suppose this is my image file. This is a black and white image. Okay, wherever I have shaded is black, the shaded part is black and the white space is white. So this is a black and white image. This is white, this is black. What will RLE see is, okay, how will my computer store? Okay, one black, one white, one white, one white. Next row, one white, one black, one black, one white. So it will store binary value for each of them. Right? Suppose binary value for black is A. Suppose we'll consider binary value of black to be A. What will RLE see is, okay, there are 3 black here, so 3A. So firstly, it identifies repeated patterns, like black is getting repeated here, and it will store in that format. Let's see how lossless compression will, or RLE will store this file. Coming on to the first row, how will it store this in binary? First row it sees one black, so one black. Right, the code, I'm writing the code here. One black, one black, 1, 2, 3, 3 white, one white, 2 blacks, one white, one white, one black, one white, one black, one white, one black, one white, one black, 3 black, one white. This is how it is going to store the code. So RLE is a more efficient method. This is how it reduces file size. Conventional method or the normal method, how a computer system stores the file is one black, one white, one white, one white. However, lossless or RLE will store it as one black, 3 white. So that reduces the amount of space the file takes to store. Well, that's it from my side. This is chapter 1. If you liked the video, please subscribe the channel. Put on the bell icon for the future videos, and we are going to cover the whole IGCSE syllabus, practice worksheets and past papers. You will find all the videos in the playlist of this channel. Go towards the playlist section. You will find a playlist for grade 10th, 9th and 10th IGCSE. and these are the videos, these are the kind of videos you will find. If you like the video, again subscribe the channel, and don't forget to, if you want to find this worksheet, the link is there in the description. You'll find the link of our WhatsApp community. We have a community of IGCSE forum. It's CambiHub, right? The channel is called CambiHub. Our forum is CambiHub. We've solved doubts for free on our community, so you can click on the community, join the community, chat with friends, chat with us. We would be happy to solve your doubts, maths. So we have 14 subjects, IGCSE subjects. You can go there, find your subject, ask your doubt. It's free. We organize training sessions, we organize doubt sessions, and when exams comes closer, we do also organize doubts sessions on Zoom and Google Meet. So that is a very good opportunity. And we also have a drive links. We have our resources. You will find the link for the learning portal and our channel in the description below. You can go any one of them, right? If you go to our WhatsApp channel, it's a WhatsApp community, you can join that. Or you will also find the link of our drive resources or the CambiHub's learning portal in the description below. This is Pranay signing off from CambiHub. I'll meet you in chapter number 2. Bye bye.